Hello everyone, welcome back. Last time we started to look at some problems with Newton's laws, some different forces. We looked at frictional forces. We're going to continue with that today, but I want us to keep in mind a kind of two separate kinds of problems that will help us understand what's going on and how to approach different problems. The first kind are called static or equilibrium problems. Now, these problems are those where the net force acting on our object is zero. Likewise, if the net force is zero, the acceleration is zero. That means the velocity is constant, but often it means if the object starts off stationary, it continues stationary. It doesn't move. It maintains a zero velocity. So not always will the velocity be zero. For these problems, this could just mean a constant velocity, but for many problems that we'll look at, it will mean a stationary object. So for the moment, let's imagine we're looking at stationary problems in this case. So we've got static problems, equilibrium problems, where the net force acting on the object is zero, and the object is remaining stationary. It's not moving. We can go either way using this information. If we know the net force acting on an object is zero, that tells us the acceleration is zero, it's not going to be moving, or with a constant velocity. On the other hand, we know if it is not moving, we can go the other way and assume, well, that means that the net force has to be zero. So we can go both ways. If F is zero, that tells us A is zero. If A is zero, that tells us F is zero. Now, the other kind of problems are the dynamic or non-equilibrium problems. These are those where the net force is not equal to zero. In this case, with F equals ma, we know the acceleration is not equal to zero. This tells us we've got some motion for our object. The object will be accelerating. So when we have a problem, a stated problem, one of the first things we want to try and figure out is, are we talking about a static problem or a dynamic problem? Are we talking about one where the net forces are zero or where the net forces are not zero? Last time we looked at different kinds. We looked at both of these. We looked at an object that was initially stationary and a force started pushing on it, and if the force was not strong enough to overcome the maximum static frictional force, it did not move and we had a static problem. However, if the pushing force was larger than Fs max, there was enough force to start it moving and we would have a dynamic problem and we would have a non-zero acceleration. Well, we're going to look at some more problems like that. However, rather than a horizontal surface, we are now going to imagine that we have an incline. What happens when we have an incline problem? Well, let's just imagine. I'm going to incline this surface at an angle, and I want you to tell me, is this thing going to slide or not? So I'll turn this up, I'm going to let go. What's it going to do? Will it slide or not? Well, the fact of the matter is, we don't know. If I incline it at a very slight angle, it will not slide. However, if I incline it at a steeper angle, it will slide. So whether the object slides or not will be dependent on how much friction there is, and the amount of friction will be dependent on the angle. What do you think? The coefficients of friction? So let's take a look at this very carefully. Let's imagine we've got an incline with an object with a mass and coefficients, and let's see what happens. Let's imagine that we have a mass of 12.5 kilograms on an incline, and let's assume that incline is at an angle of 10 degrees with the horizontal. So it's 10 degrees above the horizontal. Let's assume we've got coefficients of friction, coefficient of kinetic friction, mu sub k, 0.120, coefficient of static friction, 0.210. Well, let's figure out what's the acceleration of the block. The whole problem then is to try and figure out what is A, what's it going to do? We first need to decide, is it going to slide or will it not slide? Do we have a static problem or do we have a dynamic problem? To do that, what do we need to draw? We need to draw a free body diagram. So let's do that. I'm going to draw that over here. What's a free body diagram? It's a diagram that includes all of the forces. So we need to draw a diagram with all of the forces acting on the object. Just what's the object? What's the physical body in the problem? on which we're looking at the forces? This block, whatever it is on the incline. Okay, let's do that. I've started the free body diagram over here. We've got the object on our incline. The incline is 10 degrees to the horizontal. What forces are acting on the body? Well, first we know the weight. We need to draw these in, and we need to be very careful about drawing them in the correct direction. What direction is the weight? The weight is always straight down. So we've got a weight acting on the object straight down. What's the magnitude of the weight? mg. We know the weight is mg. We'll stick the numbers in just a second. What else? What other forces are acting on it? It's on a surface, so we have a normal force. What direction is the normal force? Remember, normal, what does normal mean? Perpendicular. So the normal force is perpendicular to the incline. So the normal force is not straight up and down, it's perpendicular to the incline that way. So there's our normal force. What else? Do we have anything else acting on it? Well, there's probably going to be some friction. What direction is the friction? Well, gravity is trying to pull the block down the incline. We'll assume for this problem that the block is initially at rest. Maybe it slides, maybe it doesn't, but at least initially it starts out at rest. The friction is trying to work against, so to speak, the gravity pulling it down the incline. So in what direction is friction? The friction is going to be up the incline. So the friction is this way. What kind of friction? We don't know yet. We don't know whether it's going to be static or kinetic. It'll be static if we have a static problem and the block is stationary. It will be kinetic if we have a dynamic problem and the block starts to slide. To figure out what is going to happen, we need to break these down into components. We need to use Newton's law, F equals ma, and to do that we need to break these forces into components. So to do that we need a coordinate system. You might think, well, let's just choose our old xy, horizontal and vertical. However, it turns out it's actually easier to adjust these coordinates to align themselves with the incline, along the incline and perpendicular to the incline. Why do we do that? If we think about what's going to happen to this block, if this block moves at all, it's going to slide down the incline. We know it's not going to move perpendicular to the incline. There's no motion perpendicular to the incline. If it does anything, and it might not even do this, but if it moves at all, it will move along the incline. Well, that tells us that no matter what happens, we know that there is no acceleration in the direction that's perpendicular to the incline, which means we know the net force must be 0 perpendicular to the incline. So let's take advantage of that fact and define one of our coordinate axes in that direction. We'll define our y-axis perpendicular to the incline. That tells us at least we know we have a static problem in the y direction. We must have the net force in the y direction equal to 0 because we know the acceleration in the y direction has to be 0. So along with that, we will define our x-axis perpendicular to that. And because if we have any motion at all, we know it will be down the incline. We'll define down the incline as our positive x direction. There are our coordinates. What we need to do now is to break our forces down into components and see what we can solve from that point. The first force that we'll decompose is the weight. Now the weight is straight down, so the weight is in this direction. What we have to do is break the weight down into its x part and its y part, keeping the weight vector as the hypotenuse of the triangle. We need to break that down into a part that is perpendicular to the incline and a part that is along the incline. Now I've taken that triangle and drawn it a little bit larger down here. So we've got the weight, which is the hypotenuse of the triangle, and then we're drawing the two sides that are perpendicular to each other. The one side that is perpendicular to the incline in this direction here is here, and the side that is down the incline here is this side. The side that is down the incline, we'll call that W sub x, the x component of the weight. The side that's perpendicular to the incline, we'll call that W sub y, the y component of the weight. How are we going to break this down? Let's look back here at the angle. If we know that this is 10 degrees and the weight is vertical, in other words, it's perpendicular to the horizontal, if that's 10 degrees, what's this angle here? Well, it's a right triangle, so we know that must be 90 minus 10. In other words, this must be 80 degrees. Now, what about this angle in here? In other words, this angle down here. What is that? Well, we know that this component, the y component of the weight, is perpendicular to the incline, so we know that this whole angle here must be 90 degrees. If that is 80 degrees, that must be 90 minus 80 degrees, or 10 degrees. So we know that this angle must be 10 degrees right there. Just go back over that once more. We know if that's 10, this angle must be 90 minus 10, which is 80. And then this angle in here must be 90 minus 80, which is again 10. I think you'll see that no matter what angle this is, that is going to end up to be the same angle as that one. That's 10 degrees, that's 10 degrees. For another triangle, another incline, if that were 15 degrees, that would be 15 degrees. If this was 27 degrees, that would be 27 degrees. Whatever that angle is, that's going to be that angle there. So what are our components? What is the x component? Notice the x side, the x component, is opposite our 10 degree angle. Opposite goes with sine. So W sub x is the weight, the hypotenuse, which is mg, times sine of our angle. And I'll just write it as theta for the moment. So the x component, usually think of x, oh, x is always cosine. No, it's not. You've got to look at your triangle to know what sides go with which trig function, sine or cosine. In this case, the x component is opposite the angle, so W sub x is mg sine theta. What about the y component? That is adjacent to the angle, so we have W sub y is mg cos of the angle. Very, very good. So there are the x and y components. Let's now look at our forces. Let's figure out what is the net force in each direction. First, what is the net force in the y direction? The net force in the y direction is the sum of all of the y components of the forces. So what are the y components of all of our forces? So let's look at each force and ask what forces are in the y direction or have a component in the y direction. First of all, the normal force. We notice the normal force is completely in the y direction. So whatever the magnitude of the normal force is, that's the component. That's the y component. So how much of the normal force is in the y direction? All of it. So we've got F sub n as a force in the y direction. What else? What about the frictional force? Well, the frictional force is in the negative x direction. It doesn't have a y component. So the y component of the frictional force is 0. What about the y component of the weight? We already figured out the y component of the weight has a magnitude of mg cos theta, but notice it is in the negative y direction. So we actually should put a little negative sign in there. The y component is negative. So we need to contribute a minus mg cos theta to the y components. And what does that equal? That must equal the mass times acceleration in the y direction, which we know is 0, so this all must equal 0. Let's bring this to the other side, and what do we have? We have F sub n is equal to mg cos theta. There we go. That is something that we will see often enough that we really should probably remember that. When we have an object on an incline, the normal force is not equal to the weight, assuming there are no other forces acting on the object, pushing on it or something like that. An object on an incline has a normal force that's equal to mg cos theta, where theta, again, is the angle of the incline. Let's remember that. We're going to see that often enough. We could always figure it out again by going through this calculation, but typically we're not going to do that. We'll just remember, oh, the normal force for an object on an incline is mg cos theta. An interesting aside, what if this angle were to get smaller and smaller and smaller? What if theta were to go to 0? We would end up with our incline becoming horizontal. Well, for cosine of 0, what's cosine of 0? That's 1. Cos of 0 is 1, and that turns into the normal force is mg, which is the weight, which is exactly what we would assume for an object sitting on a horizontal surface. The normal force is equal to the weight, as long as there are no other forces acting on it, pushing it down. So it's good that this actually reduces to what we would expect for a horizontal surface. Very good. Now let's look at the forces in the x direction. We have the forces in the x direction are what? What forces are in the x direction or have a component in the x direction? Well, the normal force, that's in the y direction, has a 0 x component. What about the weight? Well, the x component of the weight, as we've already seen, is mg sine theta, and that is down the incline in the positive x direction. So we have an x component of mg sine theta. That's the x component of the weight. And then what about the frictional force? Well, the frictional force is completely in the x direction, going in the negative x direction. So we need to subtract F from our x forces. There we go. And this must equal, those are all of the forces. This must equal what? This must equal max. Does this equal 0 or not? We're not sure. What we have to do is compare what will determine whether this is 0 or not. This will be 0 depending on how large f can be. If f is large enough to balance mg sine theta, then the acceleration will be 0 and the block will not slide down the incline. If this is not large enough, it will not slide down the incline. If it is not large enough, it will slide down the incline. Well, how big can F be? What's the largest value that the frictional force can have? The largest value is when it's equal to Fs max. So what we have to do is we have to calculate how large is Fs max, how large is mg sine theta, and compare those two. And that will tell us whether we have a static or a dynamic problem. In other words, will the block slide or will it not slide? So let's calculate those and figure out what we've got.